Now we want today to first focus on non-standard views like section view, auxiliary view, broken out view, and so on, detail view. And then we'll focus on the idea of tolerance, okay? So first, section view. When your part has some details inside or hidden, that when you want to project them on the main three views, they always appear as dashed lines, as hidden features. One way to see better inside the part and render those hidden features as visible is to cut the part with a plane into two pieces and then look at one of these pieces. So here, if you consider this part and this cutting plane, it basically chops the part in half, and if you look at the part behind the cutting plane, those areas of the part which coincide with the cutting plane, which are on the top of the cutting plane, those we basically, to show that it's a section view, we use these hatching lines, okay? These lines at some angle, all of them at the same angle, at a specific distance. And so the areas we hatch means those areas are on the cutting plane. Anything that is behind the cutting plane, we show it with visible lines, right? So for example, if we had this hole, if you look at the front view, it is going to appear as a rectangle with dashed lines, right? Because it's hidden. But now, if you look at the boundaries of this hole, you see that the boundaries here and here, they appear as what? Visible, because we can see this semi-cylindrical surface. Okay, so again, anything behind the cutting plane will be shown with visible lines. And you might wonder, what if I have some hidden feature that is behind the cutting plane and I cannot see? For example, here in this object, what if there was a hole back here, right? So if I had some cylindrical hole right here, then of course I cannot see that when I project it on the cutting plane. So what should I do? Should I show it as hidden lines in the section view? No. So that's another important rule. To avoid confusions, if there is any hidden feature behind the cutting plane, we are not gonna show it. So section views are not meant to show everything in the part that is behind the cutting plane. What we are really interested in is the areas that are cut by the plane that we hatch, and then some other details that we are interested to see as visible lines. So if there are invisibles, we are not going to put them on the top of visibles or on the top of the hashed areas. We avoid showing any hidden lines on the section view. The same was about the isometric view. If you remember, I mentioned when you draw the isometric, never activate hidden views in an isometric, okay? So these are the two views you never show hidden features. The other thing is, okay, now how do I show the cutting plane in drafting? So the cutting plane symbol is very similar to an axis. So it is going to be dashed dotted line. The only difference is at the end you have thicks, okay? So at the end the lines are thick, and also there is arrow to indicate the direction of the view, right? So if this is the top view of an object, which is basically the simple cube with a cylindrical hole in it, so when I cut it with a plane in two parts, which parts am I going to be interested in watching? The back part or the front part? These arrows would tell me I want to see the back part. Now in this case, if I see the front part, the view of that is going to be the same as this. Why? Because this part is symmetrical about the cutting plane, but that's not always the case. So let me show you the example here. So here there is this object it's the top view of an object where the cut extrude is basically half of it is a semicircle, the other half is cut by two planes. So here, if you look at the back part of the part behind the cutting plane, section AA, that's what you see. But on the other hand, if you look at the part in front of the cutting plane, BB, then you would see these two planes separated, of course, by a line because there is a break here, right? So again, if the part is not symmetric about the cutting plane, then the direction of the section does matter and the views will be different, okay? So you should always show the direction. Okay, so I mentioned that we use hatching lines to show the areas on the cutting plane, and the rest of it will be visible. If there is any invisible, we neglect it. A couple of things about the hatching lines is, first of all, the angles of all hatching lines are the same. There is a specific spacing between them. And the angle and the spacing between the hatching lines actually depends on the material. So that's another thing. Each material, depending on what material your part is made of, when you cut it, the angle and the spacing between the lines is going to be different. Now, should we memorize that and keep that in mind, like that steel has this much spacing, that angle, and aluminum is this? And no. When we do it with software, CATIA has all this info and will take care of it for us. But if you had to do it on the paper, you should be aware of them. Sometimes they even have different colors, the hatching lines. Not all of them we show with black. The other important things is the angles of these hatching lines should never be perpendicular to the edges nor parallel to the edges. Okay, so they should make this acute angle with the edges. So none of this is true. Again, do we need to do that? No, CATIA does it for me. If there are assemblies, the two parts that come into contact, like here, part 92 and 91, the direction, the slope of the hatching lines would be different. One of them is positive slope, the other is negative. Okay, so never two touching parts in assembly will have what? The same slope, because that might be confusing. But when you see you go from positive slope to negative slope, you know that you move from one part to the other. So that's another important rule when you cut the entire assembly with something. Okay, and we don't need much of a section view here. Ribs and webs. If you cut a rib or a web, you should not hatch it. So, for example, if you have this part here, where this is basically a rib, okay, then when you cut it with this plane BB and you show it from the side view, although this trapezoidal part is cut and it is on the section plane for view AA, so here this is view AA, actually not BB, AA. If you look here, although plane AA cuts all of this rib and this whole trapezoid should also be hashed, but we never do it like that. We leave it as unhashed. It's an exception of section views. And the reason is, if we do it, then it gives you this confusion and impression that this is not a rib, this is a solid connection from here to here, right? So it's a wide feature. So if I want to clarify that for you, one shape that you know well is an I-beam, right? Something that is used in structures a lot. So if I have this I-beam, correct? And I come and cut this guy with this cutting plane. And then I look at it in this direction. So what should I draw? You know, when you cut it with AA, let's say it has a limited depth. Okay, so it has some limited depth. So if you cut that, of course, the area that you're cutting is going to be an entire rectangle. So it is going to look like this. Right? But what's the difference between that and if you cut a cube? So if you cut a cube of the same size, with this plane AA, what would be the difference? Nothing, right? So if this is BB, you can say this is either AA and also what? BB. So if you basically cut a rib or a web here, this part of this beam we call web. This portion that connects them together, this thin feature. So this guy is called a web, and this top part and bottom part we call them what? Flange. So flange, when we cut, since it's not a thin feature, we hatch it. But web, the thin part, when we cut, we are not going to hatch. So this is actually, again, if I do hatch the entire section from here to here, it gives me the impression that the object actually looks like this instead of that. So what do? I said that is section BB, right? Or BB looks like this. But what about AA? So AA is not going to be like that. AA is going to be what? Only the flange part is going to be hatched because it is a wide feature. The web part from here to here, although I'm cutting it, I'm not going to hatch it, okay? So now I know this is an I-beam and this is not a solid cube, okay? So that's the reason we don't hatch with webs or ribs. Good. And there is one more thing. Let's talk about that as well, and then we go to CATIA and I'll show you how to do that. That is called broken out sections. Sometimes you do not need to cut the entire part into two roughly equal sizes. All you need is to do a local section. Why? Because you are interested in a local feature. That's where you carry out this broken out section. So broken out section is a local cut just to show a local feature. Okay, and I'll show you how to do that in CATIA as well. So now we want to go and I'll show you how to do that in CATIA, how to change the direction of the cutting plane, and then how to hatch an area, rehatch it if you want, and so on and so forth. And then there is a third kind of section, is called Breakout View, which is like a 3D cut. So let's go ahead and do all of this in CATIA. So let's say this is a part that I have, and I'm interested in cutting this with maybe a plane that is a symmetry plane or a plane that is going through mid-thickness of the back plate. So the first thing you need to have for any drafting, as you remember, is to have the part open. Okay, so you have to have the file, the CAD file of the part open. Then you go to drafting, and ANSI standard is good. We go forward, and let's bring the 3 standard views. And maybe an isometric. And then we go to the part and select the front plane and bring them all in. And then we can resize all of these views to fit them all inside the printing area. Right, so you see the size is 1:1. If we make it 1:2, probably we can get everything easily fit in. I can probably make them a little bigger too. Maybe they are too small, but maybe I make them 2:3. That is a little better. So now these are my views, and now I want to cut one of these views. Let's say first I want to cut the front view with the symmetry plane. Now, whatever view you want to cut, it has to be the active view. So the boundaries of that view should be red. So right now you can only cut the front view. You cannot cut the top view. If you want to cut the top view, you have to make it the active view by making its boundary red instead of blue. How would you do that? If you remember, you double click on the boundary. So whatever active view you have, you can cut it. So let's say I want to cut the front view. Where is the section? It is under the view toolbar, and it is the second one from the top. If you expand it, there are several types of views, but what we really want right now is the offset section view. So we click on it, and here you can draw a line that resembles the cutting plane in this view. So here, say I want this line, and whenever you're done, you have to double click, right? And you see, when I move this view to the right or to the left of my view, the direction of the cutting plane, right, those arrows, you see these arrows on the cutting plane, these guys, so they change. So let's say I want to see the left side, and then I put it on the right. So this is what I see if I cut this part, right? The middle part I cut, so it's hatched, and then this quarter cylindrical surface, I see it as this, and then this back plane, I see it as that. Now you might say, what about this hole? Yeah, this hole is behind the cutting plane. But as I said, I would not activate hidden views. If I activate hidden views right now on this section plane, on the section view, look. You see? So this guy and this one are that hole. And you also have this one for this back plane. But this is going to be confusing because the hidden lines and the dashed lines are all on the top of each other. So we never ever do that, okay? We never activate hidden lines on a section view. We leave it like that. Okay, so this is a section view. And again, you see these arrows, they show the direction of the cutting plane, right? You see here, I double clicked on the arrows. When you double click on the arrow, then you come to a different toolbar. And then you have this tool here, which says Invert Profile Direction. So if I click on this, then what happens? I can invert, make it reverse the direction of the cutting. So let's say I wanted this side, and then I reverse it, and then I say what? Go back. So now you see the direction changed. So the orientation of this part is reversed too. So that's how you invert the direction of the cutting plane. You double click on the arrows, you come here, and then look at this shape here. Then I reverse it, and when I get back, you see the direction of the cutting plane is reversed, and that's what I mentioned for you over here, right? So that is important. What if you want to move this guy a little bit to the left or right or something? Can you modify the location of this? So I showed you how to modify the direction of the arrow. What about if I want to move it a little bit to the left, right, or do something with this arrow? Well, yes, of course, I can always click on this view and delete it and redo it. But when you have something, can you go ahead and modify it? Yes. So if I, again, double click on this, I come here, and then this second tool says replace the profile. And when you click here, then let's say I want to move it here instead, right? And there we go now. Yeah. So you can modify the direction or the location of the cutting plane. So this is one thing. Now let's say here I want to cut the top view. So as I said, you have to first make the top view active like that, right? By the way, the top view should be showing your axes and hidden lines, so don't forget. Okay, you have to make sure your top view shows everything, but when you do the section of that, you don't need to show the rest of the detail on the section. So I click on the section, and now this view is activated. Then I go and put my cutting plane wherever I want. Let's say I want to cut this something like that. Okay, and then I can put this guy on the top or below, something like this. Okay, so that is a section view, and again, you make sure that your section view does not have any detail other than hatching lines and the visible areas. Okay, so this is doing a section view and modifying it. Then, as I said, we have broken out section and breakout section, right? And then modifying the angle of the hashed area. So when you have an area that is hatched, you can eliminate these lines, you can redo it and something. I absolutely do not suggest you do that, because as I said, these angles and the spacing between the hashing lines is specific to each material. When you modify it, you probably put it to a wrong value, and that's not a professional thing to do. But look, if I just do a left click, highlight them, I can what? Simply delete them, or I can double click on them and what? Change the angle of them, and change what? The pitch, which is the distance between them. So I make it smaller, I'm gonna have more hatching lines. Look, yes? So I can do it, but again, I absolutely do not recommend you do this, as you probably set it at the wrong pitch and wrong angle for this specific material. Okay, so this I mentioned to you. Now, as I said, we have broken out and breakout. So let's look at that. So the breakout view is the one that this is broken. Broken is a separate thing. We'll talk about broken separately. Broken is completely separate thing. Okay, so broken view is for long object. So breakout view, as I said, is a 3D cut. So you have to apply it only to the isometric view. So I double click here, and then I click on the group, and then here you specify an area that you want to cut, and you put that area you want to cut inside a inside the polygon. I'm sorry. So here, let's say I want to cut this area. And then it says, okay, what is your reference element with respect to what you want to cut anything? And you provide some depth if you want. If you don't, then it considers the plane that passes through your polygon as a reference. And look, it has cut the part using a plane that was fit to the polygon you draw, and it creates this cut. Okay, let me do it with a different polygon. So maybe something like that. Right, so you see this area is gone. It's not super informative. It is not super informative, especially if your cutting plane is not well positioned. So it gives you something, but as I said again, it's not super informative. Now, actually, let me try doing it on one of the 2D views as well. See if we can make it cut a 2D view. So if I go ahead here and cut this 2D view, what would happen? Well, apparently it does. There we go. So apparently it allows cutting a 2D view as well. Deal with it as a 3D view, and the reason I did that is because for this breakout section there is no command in CATIA. Okay, so there is no specific command that you can do a local section like this directly, so we have to take advantage of the breakout view. Okay, it kind of does something like that for me. The difference is it is doing it with a plane, and when you move this plane backward or forward, what happens is it is gonna cut either the entire object or nothing. Okay, so the reason I could do it here is because this portion of the part is sticking out of the part, so it could cut it like at some point here. But if I moved it further back, then you see it did cut the whole object. So this is not super convenient tool to use, but that's what we have in CATIA. So the other thing that might be of interest to you is threads. If you have a thread and you cut a place that there is thread in it, what would happen? Let me show you that as well. So we saw when we have threads, we will have 3/4 circles and stuff, but let me refresh your minds on that. So what I would do here is let me undo this cut and make it nicely back. Go back here, and here these holes are just simple extrude or cut extrude, so they are not threaded. Let's see if I can apply a thread to them and then see the difference. So if I click on the thread command, say I want to thread this hole, it says what is your limit face, I say this much, and then says thread diameter is determined automatically, And then the depth of the thread, let's say 8 units. So I'm not gonna threaden it all the way back, and pitch is 1 mil, that's good enough. So I added a thread to this, although it's a cosmetic thread, but I made the thread on this one and not on the other one. And I save it, and now I go back to my drafting. All I need to do, if you look here, you see both of the circles appears the same. Now I update first. Still no difference. Why? Because I have not activated the thread command. Okay, so I activate the thread command. And now look. What's the difference? Yes, if you zoom a little bit further, you can see the difference. Yes, this is a single circle, this is a double circle. And this guy here, this bigger circle, shows the major diameter of the thread, which is bigger than the hole. Okay, so in a standard view, that's what you can see, right? That's one way to see the difference. But what about any other view? For example, here in the top view, what's the difference? So if you see here, these are the two holes, not so much of difference, but if I activate the thread in them, now you can see it. Right? So this extra portion is the thread. Okay, and if I even do a section view also from the front view, where it passes through a horizontal, I use a horizontal plane passing through the centers of the holes, that would show itself also in the section view. So here I use my section view and I use a plane passing through the centers of these holes. And look now. Yes? So you clearly just need to turn off the hidden lines and center lines. I don't need any of them in a section view. But now you can clearly see that there is a thread on this hole and there is no thread on this one. Okay? So the threads will show themselves in section views as well. Okay. What else? So another thing we had, if you remember, is called auxiliary view. So when you have a plane type 2 or type 3, where when you project it on the main three views, you cannot see its actual size because it is always smaller than the actual size. Then if you really want to see the actual size of a plane type 2 or 3, you are going to project it on a projection plane that is parallel to the surface, but not one of the major front, top, or right. So here, for this object, I'm not gonna project it, or if I do, in addition to the front, top, and right, I also will project it in a perpendicular manner to this plane, which is parallel to the surface. And when I do that, of course, I would get the actual size. Okay? So I can do that. And that is called an auxiliary, an extra view. So that's where I can get the true length or the true size of a surface. Now, how do I do that in CATIA? So let's say I have this part here, and I want to see the size of this L-shape plane, because this L-shape, I cannot see its actual sizes in any of the views, right? Let me show you. So here, if I create the three views out of this part, right? So you can see 3, or maybe that's too big, and it's too big. Oh, I'm going backwards. Should be 2 to 3. Yes. So if you can see here, in none of these views, the L-shaped plane, I mean in this view it appears as an edge, but here and here, the L shape does not show its actual size, it's smaller. So what I can do, I create an auxiliary view. Where is that? It is under the top command next to the isometric. So that is isometry. Next to it is auxiliary view. So first you activate the view in which the plane that you're interested in appears as an edge. Here it is the front view. So you activate it, then you click on this command, and here you are going to draw the side view of the auxiliary plane or projection plane. And to do that, you make sure that plane is parallel to this edge or on the top of this edge. So here I draw a line that, as you can see, is coincident with this surface. And then what? I show it somber like that, right? And I can make it to be positioned independently. So now you can see it, right? This is the actual size of the L-shaped plane, which is bigger than this, which is bigger than this. Okay, so I can measure actual sizes over here. Not here, not here. This is called an auxiliary view. What else? A detail view. So detail view is for the parts where you want to show a specific detail, a small portion of the part in large size with magnification, so that you can show more details. Like something like this part, which is basically a if you look at this shape, this is like the valve inside the engine, the inlet and outlet valves. And you might be interested in showing some details about this corner, right? So then you zoom into that area, make it bigger, and then you might even put some dimension over there, because that portion by itself has too many details. You don't want to put all of those details on this front view or top view, right? So let's see. If I change my part here to something else, and draw something like that, at least roughly. Right, so I have made something like this, and then I go ahead and update my views here. I don't need this one. Okay, so this is, as I said, something similar to a valve, and now you're interested in showing some details over here. So you make that view active, and then you go here and click on detail view right below the section view, and then you draw a circle around the part of interest. So let's say I'm interested in this area, so I draw a circle and then bring it out and show it with a larger scale, right, like that. And if this is not big enough, then you can always make it big enough, right, because the scale is 4:3. If you make it 4:1, that would be more efficient, right? And then again, if this part, this is not really complicated here, but if it is, which for the valves they are, the profiles are not this simple, and you might show more details on that and show it with more magnification. Okay, so that is called a detailed or magnified view. And also we have broken view and clipping views. These are for long objects. When you have a long object, you might not need to show the entire view in your drafting. Why? Because it doesn't have too much of info more than a specific portion of it. The rest of it is just repeating itself, right? So if you show this small portion of this object, the rest of this is just repeating this first portion or this object, right? This T-beam. So just showing a little bit of that, or chop it from the left and right and only showing a portion of the beginning and the end, and chopping it from the middle and removing the middle part would save you a lot of space, right? Because the part is too long. So that's where you either use a clipping view or use a what? A broken view. And clipping view will basically eliminate the original view and only leaves for you the portion that you specify by a polygon. Broken view, it's gonna shrink it and removes the part that you don't want. So here between these two green lines it's gonna go, and the rest of it would remain. Okay, so that's where you see the zigzag lines. Okay, so you have two ways to chop a long object, and let me show you that as well here. So let me go ahead and make a T-beam or something. Or let's say I have some T-beam like this. And I extrude it for 500 mil. It's going to make this part long, or I can even make it way longer. Right? And then maybe there is a small hole here. And this hole has some features. Let's say this is good enough. The only thing I want to move the center of this hole maybe here, right? And then I use the rectangular pattern and repeat this hole along this edge, and every 100 mil I add one more of that, right? And also in direction 2, which is parallel to this other edge, every let's bring it to the other side. Right? So this is my object. And it is all repeating itself. It doesn't have anything special. So when I want to create the views of this object, as you can see, some of these views are too big, right? Do you see that? Yeah. So you can barely put them in the printing area because they're too long. And you might say, what's the point of showing all of this when it is not showing me much of detail more than a small portion of it? That's where you use a what? Use a clipping view or use a broken view. So let's say I want to clip this, so I make it active, then I go to clipping view, and here it is asking me to draw a circle around it, or if it allows me to draw a polygon, I just need to find the tools palette, which is not here right now, but let me do something. Put everything back. So if I click here, right now it wants me to basically draw a circle to clip it, and I can do that, that's okay. And you see here, now it is clipped, but I can also go with a polygon if I want to. But now I could clip this, and then the other one, let's apply a broken view. So here I go to this line guy here, and this is clipping view that we saw. And then here we have the broken view. Okay, so when you click on the broken view, you have to determine 2 points which show the location of the break. So I click here, make sure it's horizontal, and then click here. So anywhere between these 2 horizontal green lines would be eliminated, and the part above and below them will stay, right? So once they are good, I double click outside, and there we go. It is chopped to only the portion between these 2 guys, right? So you see, even still here, it wasn't enough. So maybe I have to chop this one more time. Here and then here. There we go. Okay, so you see by chopping line, and that's where, again, as I said, you see zigzag. Zigzag means long break. You can see a short break, I'm sorry. You can see a short break here, right? And line break is when you cut them vertically, not horizontally. So the break lines are long. But you can see I can clip it, or I can apply a broken view and squeeze everything in when the part does not have important details and one portion is just repeating itself. That's where these 2 views can be useful. Okay, so now that you have seen all different sorts of standard and non-standard views that you can create in CATIA and how to apply dimensions, now it's the time to talk a little bit more about advanced topic, and one of them is tolerance. So the idea of tolerance is this: when I have a part, especially several of them that are assembled together, how far can I deviate from what the designer asked me to make? How much of imperfection, inaccuracy in manufacturing I can have before the part is useless, right? So let's say I have a bolt and a nut, and of course they need to work together, right? The bolt should pass through the nut and be able to rotate through it. And the manufacturer, you ask the manufacturer to use the die and tap to create the threads on the shaft and inside the nut, and they made some mistake and they didn't use the exact type of tap or die, and let's say they made the drill for the nut or the thread of the knot a little bigger than what it should be. Well, how far it can work? Because you know, if the thread of the knot is too big, then the bolt cannot really be tightened in it, right? It just moves freely inside and out. So if it's really off, if it's very marginally off, it can still work, but probably you see some what we call clearance and a little bit loose of connection. But maybe that works, maybe not, depending on how much you're allowing the manufacturer for inaccuracy. They have to observe that and make sure that they make the part with that much of accuracy requested. Because if they don't, then the part is useless. You have to throw it away. It doesn't work for your application. So you will tell the manufacturer how accurate I want you to make these parts for me. How accurately you should stick to the dimensions I gave you. If I say this length of this beam should be 1 meter, if you make it 1.01, just add 1 extra centimeter to it and you don't cut it exactly, then I cannot use it. It's bad. Or if you make it 0.99, 1 centimeter smaller, still not working for me. Sometimes it might, sometimes it might not. Now, why shouldn't you ask? Why can't you ask the manufacturer to exactly make it the number you want? Because that's not going to happen in real life. You can never ever make anything exactly with all decimals to the same dimension that the designer asked. There is always error in real world. But why don't you make the tolerance as tight as possible? So if this is 1, why don't you ask the manufacturer that, hey, the maximum error that I allow you to have is 1.00001 instead of just saying 1.01? Why won't you add more and more decimals to make sure they are closer and closer to what you want? Yes, because having tight tolerances means they have to use more accurate machining and more accurate devices to measure and check, and more time to hit that tolerance. Okay? So it means more time, more accurate machines, and it means what? More money, more cost. So although to us, just adding more zeros and making it more accurate after the decimal point is a good thing, but in the real world it means cost and time. So for example, when you send something to the machine shop here at ERAU, again, if a dimension of a part is, let's say, 10 inches, if you say, hey, I want it at 10, that means the tolerance the machinist has to observe is 10 plus or minus 0.0025. Okay, so they can make it 10.025 or 10 minus this number, which is 9.975. Between those two numbers, it's good to go. But no, if you add zeros on the right-hand side, that doesn't mean the same thing. Okay, so again, let me mention it here for you. I want this part to be made, and I use the dimension tool and say, hey, this guy, let's convert it into mils or inches. Let's convert it into mils. So you say this guy is 137.81. Okay, that's the dimension that I want you to make for me. Since you use 2 decimals after decimal point, for the machinist, it means what? The max tolerance they can have is plus and minus 0.01. So if this is 137.81, they can only have 0.01 minus or plus. So it should be either between what? 137.79 and 82. Okay, so this means this much to them. And by the way, I'm showing you how to add a tolerance. So whenever you want to add a tolerance, well, we'll go over it later too, but you can go to the dimension text, dimension properties, and go to the tolerance tab, and then just add the tolerance, which you can use tol number 2, okay, or there is ANS number 2, and then add the numbers, okay. So this is how much they can be above or below this number, which is called the nominal dimension, because you provided 2 decimals. That's what a machinist here would interpret. But now some people say, well, zeros are zeros. They don't mean anything. So maybe I don't want to call this 137.81. I want to call it 137.810. So here, let me add 1 more decimal to it. Okay, don't round it, use 3 decimals. Now to the machinist, the tolerance should be half of this, right? They should hit it with what? 0.0005, or maybe I use 4 decimals. So I am not going to round it for you. I just make it 4 decimals, right? You see here, there is no number. You have to add a 0 yourself, right? So dimension text, main value. Let's see, can I add a 0 just like this? I don't think so, but yeah. No, it's going to be after. So I'm showing it with 3 zeros for values. Precision is that much. But now, look, my tolerance has 4, so it means this guy has 4. So now I have to go 0002, okay? So instead of that number, I have to go to this one. Yeah, do you see the problem? Now, this number compared to this number, what's the difference? This is 50 times smaller than that. So they have to hit a tolerance 50 times smaller than when you did it with 2 decimals. And guess what? Making an object up to that much of accuracy is extremely hard, extremely time consuming, and expensive. So we should not just add more decimals and more zeros whenever we don't need them. So it's a trade-off between how much you need and how much you want, right? Maybe you want it super accurate, yes, but in the real world it costs. So don't do it. By the way, when they make an angle for you at the RAU, they cannot do better than 1 degree. Okay, so if you add an angle, let's say here I add, although this is 90 degrees, but that's okay. When I add this angle, never go ahead and say, hey, I want this to be 90 degrees plus 0.03 and minus 0.02. They cannot make such a thing for you. They don't have any device to measure below a degree. Okay? You want something with an accuracy of a fraction of a degree. We don't have that machine at the RAU. We have it outside here, but again, they're going to cost a lot to go below a degree when they are measuring something and hitting the tolerance. So just I want you to be aware of the physical limitations in real world versus just putting a number in CAD and expecting everybody to go by that. That's not going to happen unless you pay a lot of money. So, and I mentioned that for you here. Now, how do we show tolerances? Tolerance by itself is a very big topic. There are courses offered by ASME, American Society of Mechanical Engineers, or the American Standard System, ANSI, or there are books dedicated to GD&T. By the way, you might hear this word GD&T a lot. GD&T means geometric dimensioning and tolerancing, which we are seeing just an intro to it right now. So, as I said, this topic is quite extensive, and it's a course by itself, so we are not going to see everything about applying tolerances and geometric dimensioning and everything, and geometric tolerances, which we'll see in the next PowerPoint. So we'll just see an intro of that, but if you want, you can refer to ASME and get a book from them, a training session, a workshop or something, and learn a lot more about GD&T. Okay, so we just touched the surface of this topic. Now, first, how do we show the tolerance? Okay, when we have a dimension, how do we show the tolerance? There are several ways. One is called a general note. So general note is typically what we show in the frame and title block. Remember when you made the title block, I said that you have to have a note. And in the note, you say that all dimensions are in millimeters or inches, and all tolerances are plus minus that much for the dimension, for the decimals, and plus minus so much for the degrees, angles. Okay, so you can put a general note next or inside the frame and title block. And you say unless otherwise specified. So what does it mean? It means, well, in this drafting, there might be 50 dimensions. The tolerance for all of those 50 dimensions is plus minus 0.02, unless I say it's different. So for example, again, if there are 50 dimensions, you're not going to show this plus and minus thing on each and every one of them. Okay, you're not going to show this tolerance on each and every one of the dimensions and say all of them are that much unless one of them is different from the others. In that case, yes, I'll show the tolerance on that dimension. If I don't show tolerance on that dimension, then the tolerance for that dimension follows what? The general note in the frame and title block. So that's one way to do it, and I'll show you right now. You can refer to the tolerance used in another document. You say, this is an assembly, and this assembly has 10 parts. So how many draftings should I submit to the manufacturer? 11, right? One for the entire assembly, and then 10, one for each individual component. So maybe in the first page, in the first document, you provide the tolerance, but now in the next one, from drafting 2 all the way to drafting 11, you might not need to show the same note or the same tolerance in each and every one of them. Say, hey, all of these documents, they use the same tolerance in page 1, on page 1, or in documents number 1. But if you want to show the tolerance directly on a dimension, there are 2 ways to do it. One is called the limit form. The other one is called the plus minus form. The limit form actually is like this. You show the max and the min dimension that the manufacturer is allowed to have. Okay, so you say this side, you can make it between 1.24 and 1.26. This angle is between 31 and 33 degrees. The plus minus form, you show the nominal dimension, 1.25. That's what you want to aim and shoot for, but you can be off by 0.01 plus or minus, or you can be off on the upper side by 0.01, but on the lower side you cannot be off. In other words, you have to always make the part at or bigger than 1.25. You can never make it smaller than 1.25, okay? So limit form, plus minus form. Which one I recommend you do? Plus minus. Why? Because in the limit form you never see the actual dimension that the designer was shooting at, right? You never see the what we call nominal dimension. And it's not always the average of the max and min dimension, upper or lower limits. That's not always the case. So if this is 1.24 and 1.26, it doesn't mean the nominal was 1.25. In this case, it is, but look at this one. It's 1.25, 1.26. So you might say, well, the designer wanted 1.255, right? No, he wanted 1.25. So I really prefer not to use the limit form. I'll show you how to do it, but I do not recommend you use that. I recommend you use the plus and minus form because it shows the nominal dimension and the amount of deviations. Now, the plus and minus form has different ways. One is called bilateral. So bilateral means the plus and minus form, none of them is zero. So this is plus 0.01, minus 0.01. But the amount of deviation for positive and negative are the same number. So positive 0.01, negative 0.01. So we say it's bilateral, means your final dimension should be bigger or smaller than the nominal. Bilateral, you can go either way. But the amounts that you can go either way, the amount of deviation max is the same. So it's called bilateral equal. If the amount of positive and negative are different, we call it bilateral unequal, and sometimes it's unilateral. Why? Because one of these deviations is zero. So you can only make your part at or bigger than the nominal, or if the positive is zero, the negative is non-zero, means you can only make the part to be at or smaller than the nominal dimension. So we have unilateral, bilateral equal, and bilateral unequal. And except for bilateral equal, for these two cases, unilateral and bilateral unequal, the average of the max and the min is never what? The nominal dimension. So you see here, if you take average of these two, that's not this guy. And then the average of these two numbers is also not this one, because these two numbers are not the same. Okay, so that's why I don't recommend you use the limit form. I recommend you use the plus and minus form. So in CATIA, the limit form is called tall-res2, and the plus and minus form is called ANS-NUM2 for the ANSI standard. For ISO standard, we use ISO alpha 1. Okay. So first, let me show you how to do this in CATIA, and then how to add a general note to the frame and title block, and then we talk about further topics on tolerances. So this is what we have. As I said, when you have a dimension, you can add plus minus form or the limit form to it. So let's say here, I provide this dimension, and if you remember, I can change the units for it, and I can change the number of decimals for it. I can change the size of the font for it, and so on and so forth, right? So let's say that's the number. Now I want to show the amount of deviation or the tolerance. So I right click on this text, dimension text, and go to properties. Then the second tab says tolerance, and here you choose the type of tolerance. As I said, ANS-NUM2 is the plus and minus form, so you can use this one if you want, and then you provide the amount of plus and minus. So let's say I want it to be plus 0.03, and then the minus to be negative 0.01. By the way, although it's lower value, you should always provide the negative here. If you don't, then it consider it positive 0.001 and positive 0.003. So it makes it unilateral. So if you want the lower value to be negative, you add the negative yourself here. Okay, like that. So this is how you add a plus and minus form. Now, as I said, the other way to do it is using the limit form, which I don't recommend, but I'll show you, as I said, how to add a limit form, and in CATIA it is called tolres2. So here, instead of method ansnum2, we'll find tolres2, which is this guy. And look. Yes, you show the upper and lower limit. Again, I don't think that's a good idea, but that's if you want to do it. Now, what about the general note? So general note, we have to add it in the frame and title block. So first we need to have a frame and title block. And remember, you could go to Edit, go to Sheet Background, and then go to Insert, and then Drawing, and then what? Frame and title block, and choose one of the default frames and title blocks made by the Salt systems, right? And you can use that. Correct? And now it's time if you want to modify it, but let me first get the right view out of the way because it is on my way. Or let's just delete it for the moment. We don't really need this guy. So if I want to edit a frame and title block, I have to go back to it and I can click on any text area and modify it, right? So remember, we modified it in the past and we added material, the mass, that's another, I said I don't really like it to call it weight, it should be mass because it is in kilogram. Then you can have a scale, you can have size of the paper, and the name of the drafting, the number, and everything, right? So one of the things that I want you to have in your frame and title block is called notes. Okay, so I want you to have something called notes. And in the notes, I want you to provide this general note that unless otherwise specified, all dimensions are in inches, right? And let me make it a little bit smaller. Yes. And then also you add something for the tolerances. Okay, you can always move this line a little further down. All right. Right, I can do all sorts of things that I want. I can modify them any way that I want. And even use different lines. Not limited by this. And this is good. And so all dimensions are in inches and tolerances are plus minus 0.002, right? As you can see here for decimals, right? You see tolerances, decimals that much, angles that much, correct? So you say tolerances are decimals that much, and then angles again plus minus 0.1 degrees. Yes? So this is a general note that can be added to any frame and title block, and it will help. Instead of you putting this number on each and every plus minus 0.02, right? Instead of you adding this plus and minus 0.02 on each and every one of these dimensions, you don't do that. Only you do it on a dimension that is different from that general tolerance. If a dimension's tolerance is different than that plus and minus 0.002, then you show it on it. Otherwise, we know if you just provide a dimension here and you don't provide the tolerance for it, I know this guy is going to be plus and what? Minus 0.02 without you even adding that here. So do not go ahead and add it. Again, unless it's different. Okay, so that's called general notes. By the way, since I just talked about this frame and title block on Canvas, under modules, under assignments, there are two customized frame and title block which we made for this course. One of them is for ANSI standards, one of them for ISO, and I recommend you use those for your homework, quiz, and exam instead of the ones that CATIA, the SALT system, provides. So instead of this with so many stuff that you don't need for the sake of this course, right? Many of these are for more advanced drafting for companies and so on, like checked by, supervised by, document number, and so on. Many of these details you don't need. So instead of this more complicated frame and title block, I made for you two different simpler versions and more efficient versions for this course. So if you get this frame and title block under assignments for ANSI, you can create your drafting on this one. So here I go and open it. And this frame and title block, as you can see, is way more efficient. Right? Title, drawn by who? The topic of the course, and then a scale and notes. Or if you want, you can get rid of this and add what? Material and mass. Correct? So here, I can do my stuff on this one. And as I said, this is way more efficient than, you know what, let me open the other part. Let me use this guy. Okay. I have to do it one more time. All right. So when I want to modify this frame and title block, again, I go to Edit, Sheet Background, and I put my info here, right? So I say, well, the title is Project 2. By the way, it is really your Project 2 file. Drawn by me or you. And then here, if you don't want this, you make it what? Mass in kilogram. Say it is 1.02. Right? As I said, you can feel free to modify it to any way that you want. And then you can add one more. And here you say material is steel, right? Or aluminum or whatever. And you can add one more line here if you want. Right? So feel free to customize it, but this is way simpler. And then you have your scale, and then you have your notes. So you can add your note here. And if this room is not enough, feel free to make this whole thing a lot bigger. Yes? So You can modify anything you want with this, and it is way more efficient than that complicated one from the solid systems. So now you can add your notes over here, right? And whenever you're done, you just go ahead and go back to the working views and then bring your scale them all down. I always do this backwards. 1 to 3, or no, 1 to 2 maybe. Correct, and bring everything in before you do any printing. Okay, so again, I recommend use these guys that are on Canvas under modules assignment. These two are customized for this course. These are easier and more efficient to use than the default ones. Okay, so we have seen how to add general tolerance node, plus and minus form, and the limit form. Okay, now some more stuff about tolerance. One is, if you remember in the previous lecture, I mentioned that when you do the chain method for dimensioning, you are not going to show the last part of the chain. Instead, you show the overall size of the chain, right? So here, as you can see, these three surfaces, A, B, and if you call this one whatever you want, E or F. So when I did the chain method and I'm showing the offset of each wall from the previous wall, I'm showing the second wall from the first wall, the third one from the second one, but I'm not showing the last one from the third one. So I'm not showing this offset. Instead, I'm showing the entire length of the chain. And that was one of the rules that I mentioned, right? When you do chain method, leave the last part of the chain off, show the entire length of the chain. But in stack method, we did not have such limitation. Why is that? And I mentioned, I'll tell you later when we get to tolerances. So now that's the time. So why is it? So here, let's say the dimension of this one is 19, the next one is 44, and the last one is 63. Good. So, and I give plus minus 0.1 for each and every one of the dimensions, and ask the manufacturer to make it. So, if the manufacturer makes this first size more than 19, so he make it at 19.1. Okay, the max value. Is that going to affect how he makes the second offset of this third plane from the first one, 44? No. So even if he make this one 44.1, actually he made this second part be exactly accurate, right, at 25. And if he makes this one 63.1, then again, he got this third part completely right at the nominal value. So you see that the tolerances here of each one is not going to affect the next one or the overall size. So we say they do not stack up or accumulate. But that's not the case for chain dimension. What do I mean? Means if you make the first part of the chain 19.1 and make the second part 25.1, and then the third part, which in this case is 19 again, make it also 19.1, what happens to the overall size? Again, make each and every one of the parts of the chain 0.1 bigger, because you are allowed to do so, right? The designer says you can go 0.1 above, that's fine. And you do that for all of them. What happens to the overall size? Yeah, it is going to be 63.3. while what? I could only tolerate it until 63.1. So what happened? These imperfections of each, they have been added together, they stack up, they accumulate, and they will affect what? The total size of the part. Yes? Because each one is referred to the previous one, instead of each one being referred to what? The same reference. So that's why if you make these two bigger, each one of them 0.1 bigger, by leaving off the last part of the chain and showing the overall size of the chain, what are you telling the manufacturer to do? Say, hey, if you make this 1.1 and that 1.1, so far you are 0.2 up in the overall size, but you're only allowed 0.1, so what should you do to the last part? You should make it 0.1 less than 19, so it should go exactly at 18.9, such that the overall size does not exceed this much of tolerance, right? So you did make those two parts bigger, fine, but now you have to make this one smaller to stay within the limits. But here you have no limitation. You made this part bigger, fine. You made this part bigger, fine. This is exactly right. And now when you come to the third wall, you know that you should not go above 63.1 from this previous wall. So you have to exactly shoot at what? At the exact nominal dimension to keep it within the limits. Right? So here they do accumulate, here they do not. And to avoid this accumulation, we always leave the last part off and make sure that the overall dimension does not exceed the nominal size. Now, let's learn a couple of definitions. So limits are clear. In a tolerance, limits are what? The upper and the lower limits, the max and the min dimension that your feature can have. Tolerance, the actual mathematical definition of tolerance, is the difference between these limits. So here, how much is your tolerance? Yes, 0.02. Here is 0.01. Here is 0.03. So the difference between max and min dimension, right? Or the difference between the plus and minus. So it's plus 0.01 minus 0.01. What's the difference between them? 0.02. So that is called tolerance. Basic or nominal dimension is the dimension that you really want. So this 25, 19, 31, 10, this is what you really want. But actual dimension is what? What the manufacturer will give you. So you tell him, hey Patrick, do not, Patrick, you make this dimension 31, but when you get it from the machine shop, or Jeff or Jared, and you measure it with some micrometer or caliper, you see it's not 31 exactly, it's 31.02. So that's the actual size, but that's your nominal 31. And then the difference between max and min that you allowed the manufacturer to have, we call it what? Tolerance, okay? So these are some important definitions. Now, we get to the very big question. What is the big question? The big question is, where do I get these numbers? Do I just guess or what? How do I know it's 0.1 and not 0.01? How do I know here that this dimension is 0.01 plus minus, but this one is plus 0.01 minus 0.02, or this is plus 0.01 minus 0? Where do I get these plus and minuses? Where do I get these tolerance numbers? Right? You cannot just make them up. You cannot just guess. Is there any standard way to find these numbers, right? Because engineering job is not about guessing. You have to have a way to standard to follow and get these numbers. How? And the answer comes back to this topic of fitting. So when you have parts that come together in an assembly, there are three ways that these parts fit together. What do I mean? So when you put parts together, either the parts can easily get inside each other, right? They easily fit to each other, or what? They don't. You have to press them together. You have to use heat treatment or something to put the parts into each other. And then when you put them inside each other, you cannot easily separate them and take them apart. And there is some time in between that it's not super easy and the parts are not loose, easily going inside and out. And you don't really need to use a ton of force and heat to make it happen. But once the parts get inside, you need some moderate force to separate them, right? So it's not a snug fit, it's a relatively good fit. Probably you experienced that in your EGR 101, right? There were two types of pegs in a Lego, right? Remember, you had black peg and gray peg, and one of them was a snug fit, the other one was relatively loose fit, correct? So one of them was like this clearance, the other one was like interference or transition. So those type of fit will tell me how much of tolerance I need. So first, let's learn a little bit more about these fittings. Let's learn some terminologies, and then I tell you how to use this type of fit and how to use tolerance tables, and then determine what? The amount of tolerance for a specific fit and a specific dimension. So as I said, there are three types of fitting that exist in real world. One is called loose or clearance fit. What is it? That's here where two parts can easily move inside each other, okay? It's a loose fit. Like what? There are so many things, but one of them is, I want you to know about this thing if you haven't heard of it. It's called a journal bearing. What is a journal bearing? So before that, maybe we have to look at the ball bearing. Ball bearing, I guess most of you have seen or heard, right? Ball bearings are the parts where there are moving elements, in this case balls, between two cages, an inner cage and an outer cage or ring, and it allows one of them to roll on the other one. So what's the use of a ball bearing? They are used as you can see from the name, as bearings. They are used to bear a load that is applied to what? A shaft. So if you have a rotating shaft, then in order for that shaft to stay in place and tolerate the load that is coming on it, you put it on a bearing and then fix the bearing inside something called a housing. So what happens? So let me show you, if you haven't passed machine design. Maybe it's a good idea to see something here. So something like that. Let me show you some good image. Maybe the shaft. And also housing and shaft. Yes. Look at this. So here you have this pulley, and this pulley is mounted on a shaft, or here, I guess, yeah, it is a shaft. And this pulley is tolerating some load. There is some load applied to this pulley by the belt that is on it. And now you want this pulley and this shaft to be rotating in place and at the same time tolerate the load that is coming on it. So how can you make this rotation happen? So you fit the two ends of this shaft inside a bearing, okay? So a ball bearing, as I mentioned it. In a ball bearing, there are two rings. One is called the inner ring, and the other one is called the outer ring, the steel part. Shaft will go inside the inner ring, and it doesn't go easily in and easily out. In order to put a shaft inside a bearing, you need a what? You need an interference fit. What is interference fit? That's the type of fit that you need a lot of force and sometimes heat to make it happen. Why? Because the size of the shaft is actually a little bigger than the hole. So in order for the shaft to be able to get inside the hole, you need to apply heat to the inner ring to make it expand, and probably low temperature to the shaft to make it shrink, and then use force to make the shaft get inside the hole. And when the temperatures go back to normal, then the material would press against each other, and there is a ton of friction which does not allow one to easily move inside the other. Okay, so that's called the press or interference fit, and you cannot easily separate them, as I said. So that friction between the two elements allow them to what? To rotate together. So when the shaft rotates, the inner ring rotates. But inner ring rotates on what? On these balls, right? So ball bearing inside, right? So as you can see, the inner ring rotates on these moving elements, the balls, and the balls themselves, they roll inside what? The outer ring. Now, what do you do to the outer ring? Yes, you fix the outer ring inside a fixed component like these, and you call it housing, right? So the outer cage of the bearing is also fixed using another interference fit inside a fixed component we call the housing. So this way, you're allowing one shaft to rotate inside a housing by the help of this ball bearing. Good? And as I said again, you have two interference fits. One between the shaft and the inner cage, the other between the outer cage and the housing. Fine? Now, this is interference. Sometimes the amount of load on these bearings is too high, okay? The load that is applied to the shaft and the bearing is too high. It changes all of a sudden, so it's not a uniform load with respect to time. It changes suddenly and dramatically from 1 second to the next, and the rotation of this shaft is too fast. Okay? So the shaft rotates too fast, and the load applied to the shaft, which will apply to the bearing, is really high, and it changes so badly versus time, which if you want to use these ball bearings very fast, the ball bearing would wear out and it's gonna jam, because all of these moving elements inside it, like these balls, will be deformed, okay, because of all that load. They will be deformed, and soon your bearing would jam and the shaft stops rotating. Again, because of too fast of a motion and too large of a load. So what would you do in those cases? And first, where would you see such kind of thing in real life? An example is in the engine. Inside the engine, on the crankshaft, okay, so journal bearing crankshaft. So when you have this crankshaft, you know, on the crankshaft inside the engine, crankshaft is connected to what? Yes, it is connected to the conrods, right? This is your crankshaft. They are connected through conrods to the pistons. And this crankshaft should spin in place. So what happens inside the engine? When the fuel and air mixture explodes, right, because of ignition, because of the spark, then it applies a huge explosion force on the top of the piston. The piston applies that force through the conrod on what? On the crankshaft. And crankshaft would apply that load to what? To the bearings it is mounted on. And these explosions happen very fast. And then when this piston goes down, the force goes down because the expansion happens. So the force does change versus time. When they come up again and the explosions happen again there is another force. So if you plot the force applied to the crankshaft versus time, it's going to be a bunch of spikes, right? So if I could plot the force applied on the bearings of the crankshaft versus time, you see something like this. A big spike, then another big spike, then another big spike, then another big spike, and so on and so forth. Okay, and each one of them happens when an ignition happens. So this is a cycle of ignition. So because of this change in the force, those bearing elements would easily wear out and they would get ruined very fast because of something that you will learn in your machine design is called fatigue. They will get exposed to fatigue and they will get wear out very fast. Okay, so ball bearings cannot really be used to mount a crankshaft inside the engine. And that shaft is also spinning at several thousand RPMs, right? It's rotating very fast. So what do we do? How do we mount this crankshaft on what? On the engine body, right? On the engine block. How do we do it? We use something called a journal bearing. And what is a journal bearing? So journal bearings are basically, if you can see them, journal bearings are like holes, and the crankshaft is smaller than the hole. So this time the crankshaft is not, the size of the shaft is not bigger than the hole, is smaller than the hole. Of course not this much smaller. This is just magnified for the sake of visualization. So there is some gap between the shaft and the hole. So the shaft can easily move inside the hole. We call it a clearance or loose fit. And then in order to avoid the shaft hitting the body of the hole and destroying it, there is a lubricant, there is oil in between them, and this oil is under pressure. Okay, and also the body, the inner body of this hole is also covered by a type of alloy that is really resistant to corrosion and erosion. Okay, so we call them bushing, like these. So these two pieces of alloy, these two semi-cylinders, will come and get what? One of them comes cover the top part, one of them covers the bottom part. And as I said, they are really good against erosion. So if this guy touches them, they are not going to be wear out very fast. They are really resistant alloys. And also each one of them has what? Holes. Through this hole comes what? Through these holes comes the liquid lubricant, which is under pressure. And that pressure of the lubricant will not allow the shaft to touch the bushing. Even if it does, when the pressure of the lubricant is not too high, like when you start the engine, those bushings will not allow the shaft to touch the body of the engine block. So this kind of loose fit and this kind of bearing, we call it journal bearing. And this is complete different mechanism than ball bearing. There is no moving part here between the shaft and the body. There is no ball rotating. So because there is no moving metal part, it can tolerate a lot of load and fast RPM, and it's not going to be worn out or jammed. So this is a case of a clearance fit, this is a case of press fit, and as I said, there is a case in between them. It's called transition fit, where the shaft is not super bigger than the hole, not super smaller than the hole. So the parts can move inside each other most of the time, with some very mild case of force. Okay, you can move them inside each other, but you don't need a lot of force to move the parts within each other. So one case could be keys and keyways, okay, which you learn we use them to mount a gear on a shaft. So the size of the key and the keyway are a transition fit. So the key can be put inside the keyway and out of it, but not with a ton of force, and we don't make it too loose and too hard. So you might wonder, where is it that each one of these cases is used, right? A transition fit, a loose fit, and a how do I know? Well, some cases like these are quite obvious. Of course, here you want the shaft and the inner cage to rotate together, and of course here you don't want the shaft to touch the hole, right? So sometimes the cases are quite obvious. With some basic engineering intuition, you know this is a clearance fit, that is an interference. Transition fit is not as intuitive. So first of all, how do I know where in real world which one of these is used? Because even if you have clearance fit, you know it's clearance fit, there is not one type of clearance. How much of gap do you allow? A little bit or a lot? So there are several classes, categories of clearance, and there are several classes of what? Transition and interference. How tight do you want the gap to be? Do you want the shaft to be a lot bigger than the hole or just a little bit? Okay, so each one of them has subcategories or classes, we call them. How do I know? Well, that's where those GD&T textbooks or standards made by ASME or other standard organizations can be handy. So here I have added something for you in slide 39, and if we zoom in, it tells you some examples of what kind of fit is to be used. So for example, here you have what? Clearance fit, the loose fit. It says, where would you use this subcategory of clearance fit? So as I said, clearance fit has several subcategories, and we're going to see them like C9, D9, E9, E8, E7, and so on. So here you see it says parts which accommodate or need a gap, right? Part that need appropriate gap even at high temperature, continuously rotating part of a precision machine under a light load. And you might say, okay, like what? And here you see the example. For example, piston ring and ring groove fitting by means of a loose fit. So when you put the piston ring on the piston, it is a loose fit. Okay, and what is a piston ring? Again, I don't know how much info you have about engine, but piston rings are the rings around the piston. So if you have seen the head of the piston, you see it has these grooves, and then on these grooves sits something called what? A piston ring, and these are to keep the compression of combusted fuel and air mixture inside, and don't let it to get away and escape the combustion chamber inside the crankshaft area. Okay, so these are for sealing the combustion chamber, call them piston rings. So it says the piston and the piston ring is what? It is a loose fit of category C9. Then the fitting of the exhaust valve box, the main bearing of the crankshaft. We see the same thing that I just talked about it, the journal bearing. The main bearing for the crankshaft should be what? A category E9, okay? Or then we have transition fit. So transition fit class maybe H5 or H6. These are for the parts that have a light gap, or a precision fitting which locks both parts while the unit is used. Like what? Like fitting coupling flanges together. Like fitting a gear rim and a bus together. Like the rimmer bolt to fix the shaft of a gear pump, right? Or flexible axis coupling and a gear, right? So you can see the real life examples, and then we come down to what? Interference fit, where you need to use a lot of pressure and heat. And as I said, we call them press fit or interference fit. And maybe here, these are the very tight categories, S6, T6, U6, and X6. Here, you need a lot of force and heat to make it happen. And this is for parts like what? They are firmly coupled together. Like where? Like a coupling and a shaft. Like attaching and fixing to a bearing bush. Like insertion of a suction valve. Like the rim of a drive gear and a bus together. Attaching and fixing a bearing bush. Okay, so each one you need to know really what they are and what they do, but I guess the suction valve can make sense, right? If you have a suction valve and you insert it into something, you want it really tight to avoid any loss of compression made by the compressor, right? So for different applications, when you get the ASME standards, they tell you what category of these fittings you can use. There is also here this website which talks about these guys as well. There are so many resources. I'm just here showing you a sample chart and a sample website which talks about where to use what type of fits. And here again, you can see them here, right? And it talks about the fact that the running fit or the loose fit, the categories, we call them class RC. The transition fit, we call them LT, and the interference fit, we call them FN. And there are several categories of transition fits, okay? So transition fit has 3 subcategories. Loose fit 1 and force fit 1, and then inside this FN class, it's not just FN or RC that is loose, it's not just RC class, it has RC1, RC2, RC3, RC4, and RC5, okay? And each one, the amount of gap is different than the previous one. So it says the lower RC numbers are tighter fits, and the bigger number you go, they are looser fits. So the loosest type of fit that you can find are RC1, 5, and 6. They are really loose. And on the other hand, FN class, right, which is shrink fit, then FN goes starting from FN1, FN2, right? So you can see them. Let me see if I can go to the FN classes. Here, there is FN1 all the way to FN5, and you see FN5 are basically the hardest type of fit to get, right? There is a lot of friction, there is a lot of force and heat treatments to make it happen, correct? So RC56, the loosest, FN5 and FN4 are basically the fittest type of tolerance, and then in between them there are several other classes and subclasses like LC, LT, and L, and each one has its own numbers, LC1, LC2, and so on and so forth. So you see LC has from 1 to 11, and then there are other classes too. So there are so many classes and subclasses of fitting, and each one has its own application. Not only each one has its own application, each one has its own tolerance table. And how do we use these tolerance tables? Okay, so let's talk about it. So before I go over how to use these tolerance tables, I want to cover some definitions, and then we go and see how we can use those tables. So let me tell you about some definitions. One is called allowance versus max clearance. Allowance between two parts, or the smallest gap, which we also call MMC, or maximum material condition. It is the smallest gap that can be between two parts. On the other hand, the biggest gap between two parts, which also called LMC, or least material condition, is of course the biggest gap between the two parts. What do I mean by that? So here, let's say this is the shaft, this is the part with the hole, and these are the tolerances, or the limits, for the size of the shaft and for the size of the hole, right? So I say the shaft size should be between 1.247 and 1.248, and then the hole should be 1.250 and 1.251. So if I give these numbers to a manufacturer, what is the smallest possible gap that I can get back? Yes, if you want the smallest gap between the two parts, you need to have made the shaft the biggest and what? The hole the smallest. So you expect the hole to be 1.250 and the shaft to be what? 1.248. So the smallest gap is what? If you subtract the hole from the shaft, it's always the size of the hole minus shaft in a hole-based system. So it is going to be what? 0.002, positive 0.002. That's the smallest gap. What is the biggest gap I can possibly get? That's when the shaft is made to the smallest and the hole is made to the biggest. So 1.251 and 1.247. So there's going to be what? 0.004. Okay? And you can see those numbers here. Correct? So the smallest gap is 0.002. The biggest gap is 0.004 in that case. Right? So these are two important definitions. Okay, MMC and LMC, or allowance and max clearance. And now each one of those three fitting categories that I mentioned to you, each one of them is different in terms of these two parameters. If you have a loose fit, always the shaft is smaller than the hole, always. So the max dimension of the shaft is always less than the min dimension of the hole. Shaft is always smaller than the hole, so there is always a gap. So when you subtract the dimension of the hole minus the dimension of the shaft, it is always going to be what? Positive. There is always a positive gap. So here, this is a loose fit, as you can see. Between these two numbers, I can have a gap, and both of them exist. Both of them are positive. So you say both of these guys are positive in a loose fit. On the other hand, if you have an interference fit, the shaft is always bigger than the hole. So you see the min dimension of the shaft is bigger than the max dimension of the hole. So here, if I subtract and get my max gap and min gap, what are those? Okay, so how much is max gap, how much is min gap in case of an interference fit? So let's get those numbers. So what is the max gap and what is the min gap? So what is the min gap? Min gap happens when you have the smallest hole, biggest shaft. So it's the smallest number for the hole minus the biggest number for the shaft. And how much would you get? Negative 0.0019. And what is the max gap? What is the biggest gap that can happen? It is the biggest size of the hole minus the smallest size of the shaft, and still you see this number is negative. So in an interference fit, both of the gaps are negative. They never exist. Negative means they don't exist. Positive means they do exist. So clearance have both gaps positive, interference have both gaps negative. Transition, the biggest gap is positive, but the smallest gap is negative, right? So there is a chance that your shaft gets bigger than the hole. There is a chance that your shaft gets smaller than the hole. Both of them could be possible, okay? So if you look here, again, if I calculate these two guys, so what is the mean gap? Yes, the mean gap is the smallest hole size minus the biggest shaft size. So it is negative 0.009. And the max gap is biggest hole size minus smallest shaft size. So this is positive 0.0003. So you see the max gap positive, the mean gap negative. That's how a transition fit is. So using these two parameters, MMC and LMC, we can also identify these three types of fitting. You can distinguish between them more quantitatively instead of just saying, hey, this is loose, that is fit. No, this is how we can quantify these guys. Good. Right? Now, in the basic hole system that we always consider the size of the hole as our reference, as I said, there are lots of different classes of fit. Here we have different classes of RC, LC, LT, LN, FN. Okay, and each one of them is, these guys are sliding or running fit. These guys are all transition fits, different classes. And the last one is interference or force fit. So now let's look at an example together and see where we get those plus and minus numbers. So the example here is this. I have this part and this shaft, and the nominal diameter for the shaft and the hole is both 1 inch. Now I want this fitting to be a loose fit. And based on the design that I'm doing and the standards that I used, I know that I want this to be a class RC4. So class RC is loose, and I want it relatively good loose. Okay, so I want it class RC4. So now I give you this dimension of 1 inch nominal diameter, and I tell you the fitting I want is class RC4. You tell me the pluses and minuses for the shaft and for the hole. How much are they? That's where we go and use our tables. So these are the tolerance tables for classes RC1 to RC4. There are more of these tables, so these are not the only tables. There are a lot more of these tables. This is an example. If you want more, I have posted for you something on Canvas. So if you go under Canvas modules, under tutorials, there is this PDF file I posted for you. It's called Tolerance Hole Shaft Charts. Okay, and here you have more than just 4 classes RC1 to 4. So if you can see here, I have all sorts of different classes. Based on whether it's a shaft-based system or a hole-based system, there are all sorts of different classes. So here the nomination is a little bit different than what we have. Here the nomination is based on H6, H7, and so on, based on the fits. So the nomination again here is different. Here they are not called RC1, RC2. They are called H. Okay, cap H, cap F, and so on. Okay. But you see, basically based on each one of these categories, there is the corresponding tolerance table. If you want it for RC1, RC2 nomination, these are based on different standards. You can go back to this website, right? If you look at this website, as we just did, then we have what? Do you see them? These are classes RC1 to RC4 tolerances, correct? And then to RC9. And then here we go to the transition fits from LC1 to LC5. And then we can continue from LC6 to LC11, and then LT1 to LT6, and then what? LN1 to LN3, and then finally we have the FN class, which is FN1 to FN5. So all of these tolerances are available on this website for one type of standard, and then for the other type of standard, which uses these letters instead, we also have it on Canvas as well, okay, under modules tutorials. So in this example, I'm using the one off of this website. So the nominal dimension is 1 inch and the class is RC4. So I go to this table. In this table, on the left column, you have a range for the nominal dimension in inches. So your number 1 will fit one of these ranges. In this case, it's between 0.71 and 119. So it's here. Then you move the dimension under the what? Under the fitting class, which is RC4. So if you move this all the way down to what? Below RC4, then you see 4 numbers here. You see 4 numbers, plus 1.2, negative 0 for the hole, and negative 0.8, negative 1.6 for what? For the shaft. So what does that mean? These are those pluses and minuses. What does it mean? It means what are the tolerances for the hole? How should I write it? It means the hole that was 1 should now be added plus what? Here you see it says 1.2. Now that's another thing you have to pay attention to. 1.2 is not the actual tolerance. Okay, because the dimension itself is 1 inch. The tolerance, the deviation cannot be 1.2. The tolerance is never bigger than the dimension itself. It's way less than the dimension. So these numbers that you see in these tables, they are all millis. They should all be multiplied by 10 to the negative 3 to be used. So that 1.2 here is multiplied by 1 over 1,000. So that is the actual number. And then add it to 1. And then 0, which is 0, doesn't matter you multiply it by what, minus the number is your lower number. So your tolerance, if you want to show it with the plus and minus way, is going to be what? It is going to be for the hole, the diameter is 1 plus this number and minus this number. This is how you show the diameter of the hole. Then about the shaft, diameter is 1, but you can see that the numbers are both negative. So negative 0.1, negative 0.16. So you multiply them by 1,000, so you get 0.8 and 1.6. So this is the shaft. As you see, the shaft is unilateral. It is always less than the actual dimension. And also the hole is unilateral. It's always bigger than the nominal dimension. As you can see, the shaft is always smaller than the hole. And when is it that the shaft is always smaller than the hole? That's where you have a running or loose fit. And here, in this case, it is a mid loose fit, RC4. Okay? So that's how you get the positive and negative numbers. All I need to know is to know my nominal dimension, and I need to know my class of fitting. Those two will get me these pluses and minuses. The only thing I need to make sure is multiply all of them by 1,000. Okay? And then once I know my pluses and minuses, I put them in my drafting. Okay? So this PowerPoint is over at this moment, and I have one other PowerPoint which is not as long, and to be honest, I would rather finish this also on the top of this lecture, so we don't make two lectures here. We just combine Drafting Workbench 2 and 3 PowerPoints into one video lecture and call it Drafting 2. So I start this and I'll try to finish this very fast because this Drafting 3 is not so much detail. So far we learned about how to provide linear tolerances, right? Those pluses and minuses. If I have a dimension, how do I find these numbers and how do I show them? There is another category of tolerances which they call geometric tolerance. Geometric tolerances are different than these pluses and minuses. What do I mean? So here, let's say this is a part that you want to make, and then you want to make sure that this wall here, this vertical wall, is perpendicular to this bottom surface A. This bottom surface A that I use as reference, we call them the datum surface. And this is a flat surface that the part has, and I put it on the top of my milling machine or CNC or something. I put it on the bed. And it is flat, so I can use it as a reference. I know it is horizontal. And now I want to machine this vertical wall, and I want to make sure this vertical wall is perpendicular to what? This horizontal bed. Well, again, in real world, there is no perfection, so I might not get it perfectly perpendicular to A. I might have a little bit of deviation. How much of deviation is allowed? So some of you might say, well, I showed this with an angle. Say the angle should be 90 degrees plus minus 0.01 of a degree or so. Yes, but that's not how they show it in standard methods, because that's not the only type of geometric limitation or tolerance that you have, perpendicularity. There are other cases too, like what? Excuse me. Like straightness. I have this shaft and I want the top surface of this shaft to be straight. I want you to machine it for me very straight, and I don't want it to have ups and downs like this. So how do I tell you that? You need to make this straight. Or let's say you are using the lathe machine and you are doing cutting on a circular object, and I really want you to give me a part that is circular. I don't want you to give me a part that is like this. Okay, so I don't want you to mess up the machining. And believe me, if you are not a good machinist and work with the lathe machine, you might get parts that are like this, especially if you use your hand motion for the lateral motion and you don't use a uniform motion. You might not get a perfectly circular object. So how would you tell the machinist to get it circular, and how much deviation from a circular shape is the machinist allowed to have, right? Or if you want two surfaces to be parallel, right? If this is my reference, how do I tell the machinist that the top surface has to be parallel to the bottom with so much of deviation, right? So there are, or concentricity. This shaft has to be concentric with the other one with so much of deviation. So for these cases, which are geometric constraints, like parallelism, perpendicularity, circularity, straightness, and so on, we use a different type of tolerance. We call it geometric tolerance. And I'll tell you how we should show this geometric tolerance on our drafting. So for any geometric tolerance, we definitely need a datum, a reference, in at least most of the cases. And then the way we show the deviation is not using decimals of plus and minus. What we define is called a tolerance zone. And what is that? So if I go back to that perpendicularity, I say this is surface A, and I want this wall to be perpendicular. There is a symbol for perpendicularity to A with a tolerance zone of 0.12 inches wide. What does that mean? It means if you do not make this wall completely vertical and it has some angle, then if you draw two planes or two lines that are completely perpendicular to A, such that any point on this surface, on this machine surface, lies within these two planes or inside this tolerance zone, then I don't want the gap between these two planes to be more than 0.12. Clearly, if you made the wall completely straight up, vertical to A, then all of the points will lie between these two planes and no gap was needed, so the tolerance zone would be 0. But in reality, since you cannot make it 100% 90 degrees with respect to plane A, you might have very, very mild slope, and the smaller the slope is, right, the smaller the deviation of the angle is from 90 degrees, the smaller this gap needs to be such that it contains all of the points on the surface. The bigger this angle deviates from 90 degrees, right, you need a bigger gap to contain all of the points on the surface. So that tolerance zone is directly related to the deviation of this angle from 90 degrees, okay? And the smaller you make it means the smaller deviation you should have. Or let's say here, the case of, let's say, parallelism. So I say this top surface has to be parallel with surface A with a tolerance of 0.12. What does it mean? It means if it's not, so it's not perfectly horizontal, then if I provide two planes perfectly parallel to A, then any point on the surface should be within that gap of 0.12 inches, right? Or another one, for example, concentricity, right? So when I say I want the smaller circle to be concentric with the bigger circle, what does that mean? It means if you look at it from the side, and the two parts of the shaft are not made perfectly like this, they're made like that, so these are not concentric. Of course, this is really so bad. This is exaggerated. But if you look at the axis of basically this circle here at the end of the shaft, and if you look at the axis of the big circle, the gap between these two axes should not be more than 0.1, and so on and so forth, right? So you get the idea. Let me show you a couple of more. For circularity, if I say I want this shaft to be circular with a tolerance zone of 0.25, what does that mean? Means if I make the shaft something like that, of course, again, this is too much exaggeration, but you might make something like that if you're not really good. So if I draw two circles, concentric, at the center of this shape, and such that any point on this surface lies between the two concentric circles, then the gap between the two circles should not be more than 0.25. So that's called concentricity. And even for angularity, instead of, as I said, showing the angle plus minus some degrees, I can say if I want this surface to be at 38-degree angle with respect to A, I show the 30 degrees, but I don't say plus minus 0.01 degree. Instead, I use the geometric tolerance. I say I want this to be at angle with A. What angle? 30 with a gap of 0.4. So if this is not perfectly at 30 degrees, I draw two lines at 30 degrees with respect to A, such that any point on the surface is between these two planes. The gap between them should not be more than 0.4. So you get the idea of tolerance zone, and for some of them, like straightness, for parallelism, angularity, and so on, you need a reference. For some of them, like straightness and circularity, you don't need a datum or reference. And the way that you show it is using a box. So you use a box. Each box has several cells. The first cell is the symbol of geometric tolerance. The second one is the width of the tolerance zone, and the third one is a datum if it exists. Of course, there is more like modifiers and so on and so forth, but if we want to get into more details of that, that is going to go way beyond the scope of this class. So in general, there are more stuff and more symbols that can go inside this box, okay, like a modifier and so on. But again, I'm not going to get into all of that. Just want you to know that there are different types of geometric tolerances, and these are some of the symbols for them, like for angularity, perpendicularity, parallelism, cylindricity, circularity, flatness, straightness, and so on and so forth, okay? So how do I do that in CATIA? So to do that in CATIA, let me see if I can bring back the T-beam. There we go. So in here, I want to use the bottom surface as my reference. Say this is surface A, and then say this guy has to be perpendicular to A with so much of tolerance zone. How do I do that? So I need the geometric tolerance. So I bring in the dimension toolbar, and if I expand the last command, the first one of them is datum, the second one is geometric tolerance. So let's first set up the datum. So we click here and then click on the bottom surface and say this is my datum A. Okay, and you can give it a name, surface A, surface B, whatever you want. And then you click on the second one, geometric tolerance, and then you click on the surface of interest. You click here. You say the symbol I want is actually perpendicularity. And then I have some tolerance of 0.12. And then this is with respect to A, and you OK that. Yes? So that is how you use datum and geometric tolerance to create one in CATIA. Two more other things that we touch. One of them is called surface finish or surface roughness. So whenever you create parts, for many applications, the smoothness of the top surface or the surfaces that sit on the top of each other does matter. If the surfaces that sit on the top of each other are too rough, then there might be some holes and gaps between them, and those might not keep, let's say, the compression that you want. For example, for the engine valves, right, that I mentioned earlier for the detail view, when you have the engine valves sitting against the body of the engine, here, Okay, or maybe there are better pictures too, but I guess this one should tell me. So if you look here, let's see, is that clear for you here? Let me show you a different picture that is not so clarifying. Yeah, this is better. Let's look at this one. So if you look here, I have the top surface of the valve sitting against the body of the cylinder block, right, or the engine block, right? So if you look here, you look at this point. Let me see, can I get it into OneNote? Could be even better. There we go. Yes. So in this area, here, I have the two surfaces sitting on each other. And if the surface of the top of the valve or this part of the engine block is not smooth, when you have the explosion and you have a lot of pressure, if these are not sealed here, or if the rings of the piston with the body of the cylinder are not basically forming a good gap, sealing the gap very well, what happens? Before this guy can apply pressure and bring the piston down, a lot of it will be lost through these small holes. So here you need a really good surface for the top portion of the valve, right? So that's why if you look at the surfaces of the valves on the top, okay, they have to be machined very well. They have to be really nice, especially this conic area. They have to be machined well, and they have to be quite polished and shiny, again, especially as I said, this area. So over there, you need to tell machinists that, hey, the final surface you give me has to be quite smooth and shiny and nice. But how much? Because if you make it, the machinist to make it super, super shiny, so that when you look under the microscope, you barely can see any of these ups and downs, it's relatively smooth, then that would cost a lot. If you go small, then you might lose the compression, and when you look under the microscope, you see a lot of jaggedness, a lot of ups and downs and roughness. So how would you specify this, and how would you know how much of smoothness you can get from a manufacturing process? So first of all, how would you quantify this roughness, and how would you know what manufacturing method gives you how much of average surface roughness, so that the manufacturer can know how to finish the surface and give you the surface finish that you want? So first, how to quantify it. So if you look at, as I said, a surface under a microscope, you would see some ups and downs most of the times. And then these ups and downs, like these peaks here, we measure them from a base. So base here could be the lowest point of the surface. So if you measure each point from the lowest point of the surface, right, we call it roughness height. Then we have roughness width, which can be defined as the distance between one peak to the next. So we have roughness height, the height of each peak from the base. Roughness width, the distance between, is like a wavelength, basically. Not a wavelength, actually the waviness width is like wavelength. So this is the distance between two peaks. And then these ups and downs are not all the same. So not the height and the width of these peaks are all the same, especially the height of them. They are not all the same height from the base. sometimes they are repeating a pattern. They are making a pattern. It's like there is a wave. If you connect the tip of all these points together and you plot it, it might look like a sine wave or something. Then for that case, we can define a waviness width, which is like a wavelength, the distance between one point to a similar point, and then a waviness height, which is the max roughness height of all wave compared to the base. So these two correspond to amplitude and wavelength of an oscillation. But we also have roughness height and roughness width for each individual one. And then we have a lay direction. So not always these roughnesses are like this, parallel to one surface or perpendicular to the other. Not always they are like that. The way that the parallel lays are determined is by the type of the machining that you use. Okay? So sometimes, as I said, you will get these parallel lays, but not always. Sometimes you get what? Basically concentric lays. Sometimes you get lay in two directions that we show with letter X. Sometimes you get in a variety of directions, so we use M. Sometimes you get radial directions, use R, and sometimes there is no particular direction, so we use P for protuberant. Okay, so there are different ways that, based on the manufacturing method, you can get different directions of lay. Like, for example, where do you think in real life you would get concentric lays if you see under microscope? Yes, this is for a rotary machine. Like what? Like lathe. So if you use the lathe machine, clearly, if you see it under microscope, you see concentric ones. But if you use a milling machine, which is doing a surface cutting, most probably you would see what? You would see a parallel or a perpendicular one. Okay, so again, the manufacturing method will tell you the direction of the lathe. Good. So we learned some terminologies. Now, how do we tell the machinist how much of roughness is allowed? How do we show it in CATIA? So the way to show roughness, we use this symbol which looks like a square root basically. And this square root can contain all of this info in it: surface, roughness, height and width, waviness, height and width, and lay direction. All of these 5 quantities can be put on this square root. How? This is the standard. So above this square root on the left, you show the average of the roughness height. So as you paid attention, not all of these peaks are the same roughness height. So if you give an indication of average of them, you can put that average here. By the way, this number that you see, it's not whole unit. It is micro. So if everything is in inches, this is 1.6 micro inches. Remember the tolerances in those tables, they were millis, right? 10 to the negative 3. This number here that you put, it is always in micros, okay? It's 10 to the negative 6. So the amount of average roughness of the surface is 1.6 micron. Then if there is waviness, you can provide the waviness height dash waviness width on the top. Below the square root, you can provide the roughness width, and also you provide a symbol for the lay direction. So this is the standard to do it. Now, most of the time, we don't know or cannot provide any number for waviness and for the roughness width. So most of the time, what we really care about is the roughness height, the average of them, and the lay direction, especially this guy. So most of the time you see something like that appearing on a surface. So if you see something like this, and here even the lay direction is not specified, all it's saying is the average roughness height that you give me back should not be more than 63 micro inches. Okay? My calculations showed that if you have more than that, then I would lose compression. Nothing more than that. So for this number, where the designer got this number, they got it from their fluid calculations or finite element analysis. There is no table. But there is a table that can tell the machinist, okay, now that he wants this much, not more, at most this much of roughness on average, what manufacturing method can I use to achieve this? And that is in a roughness table. So this roughness table will tell you in which range of roughness height each manufacturing method can provide for you. For example, if you cut something with flame, right? If the way that you created the surface was you cut an object in half and you created two surfaces, then what is the average roughness of the surface when you did flame cutting? Well, this one tells you if you are looking in micro inches, you can go anywhere in this blue-white, light blue band, between 250 to 2000 micro inches. Why there is a band? Because it depends on who is using the tool. If you are an advanced machinist or an advanced user of the tool, you can achieve numbers like 250, smaller roughness. If you are a rookie and you have never used it, you might go as rough as 2000. Okay, so this white-blue band is in general for different type of users, especially rookies, which they can have oscillations. I mean, if you are not a pro, sometimes you might do a good job, sometimes you might not. So the band of numbers within which you can achieve could be quite wide. If you are a pro, okay, and you are less susceptible to change from one work to another, one job to another, then you would do probably the dark blue band. Okay, so this is where you have more precision and you're trying to, not more accuracy, more precision, and trying to stick to the same quality all the time. Anyways, the average of the white or dark blue band is the same point, so we use that average and say, hey, if you use flame cutting, the average roughness of the surface you can get is about 750 micro inches. So if you want 63, like this one says, forget it, you cannot use flame cutting. So I need to go and look at the methods for which the average of the band, the middle of the band, is what? At 63 or to the right of 63, which means less than that. So which one of these methods have an average band of 63? So none of these guys on the top. So this one and this one do. What is it? You can use a broaching if it's a hole, or rimming, or let's say here you can use this guy as well, which is electrochemicals. And of course, if you finish a surface with electrochemicals or with electrolytic grinding, which gives you an average of 10 to 12 microinches, very nice poly surface, of course, you know, this method is going to cost a lot more than just grab a torch and cut the object. Okay, so as you go up here, the cost goes up. As you go down until this point to this super finishing, the cost goes up, but the quality goes up at the same time. So this table would tell the machinist which finishing method they should use to achieve the number you gave them. Okay? How do we show surface finish in CATIA? So let me show you. So if I say, well, this surface here sits on something, or this surface sits on something, provide an average of 40 microinches roughness height, and with a parallel lay, or with a perpendicular lay. How do you show it on the surface? So for the surface finish, it is not in the dimension toolbar. It is actually in the annotation toolbar, and that's this guy between T and table. So you click on the surface, and then here you provide the average roughness height in microns. By the way, when you say 40, it is 40 microns, so you don't need to write it like this. And you don't need to say 40 microns. You don't need to do any of that. Just say 40. They know it is 40 microns. Then you, of course, need the symbol of the parallel or perpendicular or whatever lay it is. And as I said, you can provide the roughness wet and the waviness height and waviness wet, but we don't need to mostly. Basically, the symbol of the parallel lay, and most importantly, this average roughness height is sufficient. And there we go. Yes, so that is how you show the surface roughness. Again, to get this number, you need to do some finite element and most of the time advanced engineering analysis. Okay, so getting this number, how you got this number, it is way beyond this course and it depends on application. But this number tells the machinist which finishing method to use. Finally, again, I touched this topic. It's called welding. Welding is a big topic by itself, and in machine design course, there is one chapter entirely on defining welding and design of weld and everything. So when you want to attach two parts using welds, you just don't grab basically an arc welding machine or gas or something and go and get them attached. Okay, the type of the material to use, how you use it, how much of length you do the welding and everything, they all have calculations. Okay, and it is a sophisticated thing, the type of the weld bit and everything, and the amount of info that goes on a welding symbol, which is like a leader with this two ends, two lines at the end. This has a ton of info on it, so it is beyond the scope of this course for me to go over welding in a lot of detail. I just tell you some basics, like different types of welding beads. These are some of the common ones that you see here and there. Like if you attach two parts with this triangular cross section of the weld bit, okay, you call it a fillet weld. You might put two parts head on and then attach them like this. You call it the square butt weld. You might have a single V-butt weld, double V-butt weld, single U, double U butt weld, single bevel, and double bevel butt welds. So these are the symbols for different type of welding beads that you can have, that you have to specify. And then the other things is, if you don't do a continuous welding, you do it in patches. Okay, this is the most general case. So if the welding has several patches and each patch is 2 inches long, and then the distance between each patch to the next is 4 inches, and then the thickness of what? The cross section of the fillet weld, these two sides of this right triangle are 1/4 inch each, right? How would you show that to the manufacturer when they want to do the welding? So you use this leader symbol, and then you say behind the symbol, so this triangle is the symbol of fillet weld. Use a 1/4, right, 1/4 on the back side, which means the thickness of the weld bit. Then you say 2-4. So do what? 2 inches long each time and with the spacing of 4 inches. And then you might have noticed in this example here that these numbers and shapes can go above the horizontal line of the leader or below. What's the difference? The difference is this. If they go above above, it means, and you refer to somewhere, so you're showing somewhere and you go above the horizontal, it means actually the welding has to be done on the other side. So above means the welding is on the other side that the leader shows. If it's below, it means on the same side. So below means on the same side, above means on the other side. If it's on both sides, then use what? Both above and below means on both sides. Yes? So again, I'll show you a simple example, but by no means I intend to teach you all about welding. It is just touch on the surface. So here, let's say I want to tell the welder, the manufacturer, to weld both corners here and here with a butt weld of 1/4 inch thickness and then several patches, each one 2 inches and a gap of 4 inches between them. So how do I do it? This is the way you do it. Use the welding symbol, which is under this roughness, and then you refer to the 2 edges defining the corner, and you set up the leader, and then here you provide what? The symbols. So you say I want a what? A fillet weld on the other side, and then what? On this side. So I want it on both sides. And then you provide what? You provide here behind them the thickness of the weld. 1/4 inch is the side of each part of this triangle. And then I want 2-4 on both sides. Yes, and you okay that. So when the guy sees this, they know that they have to do a fillet weld on both sides, and these are the length and the spacing between the welds. But there are more, as I said, like that 2 lines at the end, there is a circle at the end, and there are too many things that you can see in this window that we can define, okay? There are a ton of things that we can do. What is the flag? What is the circle? So there are a ton of things, right? What is this guy? So I cannot get into that because it's way beyond this course. Okay, so I guess at this point I have touched some of the more advanced topics, including surface roughness, geometric tolerance, and welding symbols. And in more details, we discussed dimensioning, drafting, and moderately enough linear tolerances. So this is our last formal video lecture, and I'll see you more in class. Thank you so much.